Hello, and welcome again to Chapter 15, Lecture 12. We're now going to be looking at Learning Objectives 4 and 5. So we're going to be looking at our state functions and how they differ from path functions, and then we're also going to be looking at enthalpy. Okay, so when we talk about the internal energy of a system, there is no way to know the absolute internal energy of a system. There are so many ways, since internal energy is all the heat and all of the work and who knows what else. There's no way of really knowing the absolute amount of internal energy that a system has. So we kind of reference our energies to what's considered the normal or the most thermodynamically stable state for an element. So we can reference our compounds and molecules to that most stable state, which would be considered our elemental form. So our elemental form is our natural state of our elements, and we can compare to those, but we still don't know anything about what the actual internal energies of any of these things are. But it's okay, because what we do is instead we calculate delta E, which is just a change in energy. This we can determine. This we can look at through changes we can actually observe. We can't see the beginning or the end, but we can look at the observed change between one state or the other, and we give certain things arbitrary values that we can then compare to determine that change in energy. So we do our change in energy, E final minus E initial, where these values are going to be coming from, again, that whole idea that our elemental form has an energy or an internal energy of 0, even though that's not, the actual value, but that's just our reference point. Now, having said that, if our change in energy depended on more than just a final and initial state, this would not work. But because our change in energy only depends on our final and initial state, this is a thing we can actually calculate without knowing absolute internal energy values. So this idea that we can calculate something using only the final and initial state is kind of the defining thing that we see with our state functions. So a state function is a function that only depends on the final and initial states. So it doesn't matter how we got to our final state, doesn't matter what path we took to get to our final state, our change in energy will only depend on our final and initial state. So we would say that internal energy is a state function. There are other state functions, including enthalpy, which is a uppercase H, and entropy, which is an uppercase S. We're going to look at enthalpy today, entropy in the future. Okay, so we would say that our internal energy is considered a state function, and how does this vary or differ from a path function? As I said, a state function is independent of sample preparation. While a path function is path dependent. As in, it depends on the preparation of the state. So the property depends on the preparation of the state. Okay, so the path function doesn't just depend on initial and final state, but additional parts. So if we think about someone going up a mountain, okay, the amount of work and heat they expend depends on what path they take. So they can go straight up, or they can go choo, boop, choo, boop, choo, boop, choop, choop. And that will change the amount of work and heat that is used in this. So because one path goes all the way around over and over and over again versus one that just goes straight up, they're going to have very different paths. And you could also be like, okay, go up and then back down. That's going to be a different amount of work and heat than if you went around like that. So if you take your mountain, you go all the way up the mountain, then back all the way down the mountain, versus starting on one side of the mountain, going around the mountain and going to the other side, those will be different amounts of heat and work. However, your initial state and your final state, in both cases, will be the same. So a path function, even though the initial states and final states may be the same, you have to take into account how you prepared that state. So we would say that heat and work are path functions. Okay. While our energies, our internal energy, our enthalpy, our entropy, those are all state functions because they only depend on your final and initial state. So our enthalpy, as I said, that was given the uppercase H as a symbol. This is a state function. So we can determine our delta H by taking our H final minus our H initial, right? And we say that is a thermodynamic quantity equivalent to the total heat content of the system. So it is related to heat flow. I should say of a system, sorry. Is related to heat flow. So while heat is a form of energy transfer from a higher temperature to a lower temperature, enthalpy is the heat transfer at a constant pressure. So it's the heat added or lost from the system, and that would give you what your enthalpy change is. Okay, now, as I just said, with a constant pressure system, so if we have a constant pressure system, or state, the heat absorbed or released equals the change in enthalpy. So our heat, delta H, is equal to our heat at a constant pressure. And this is most processes we look at are constant pressure systems. Another way that we can calculate our enthalpy, or the way that we calculate our enthalpy, is our heat is equal to our energy, our internal energy, plus the product of pressure, volume, work. Okay? So, again, we're almost always looking at changes. So let's think about what happens as things are changing, but we're actually keeping pressure constant. So what happens as we keep pressure constant, but we change other things within here? So we look at this through pressure volume work. So again, we're talking about reactions. Reactions don't do a lot of work. The only work that is generally done in a reaction is the expansion or compression of a gas. So again, if we think about a cylinder, we've got a cylinder, and in this cylinder we have a reaction. If this reaction produces a gas, so if it produces a gas, then we're going to increase the volume in here because we're keeping pressure. So we're able to move this little cap right here. So it will go up because the reaction is going to be pushing on it with that expansion of a gas. So our reaction creates a gas. So a reaction will push up on this disk and it will expand. Like so. So in this case, work was done by the system. So our change in volume is positive, and work was done by the system. We can have the opposite thing occur, right? So we can have a reaction that consumes a gas. And as that reaction consumes gas, in order to maintain pressure, we'll actually push down from our system from our surroundings onto our system, and we will get a compression. In this case, our delta V is going to be negative, and work was done on the system. Okay, so our delta V is really the only work that we're going to have in our reactions, and it is V final minus V initial. And we can solve for that work by saying work is equal to negative P delta V. So that right there. And the way we think about it sign-wise, so if our delta V is positive, like we see in our first scenario, then our work is negative, which makes sense because work is done by the system. So we have lost energy in this case. And then if we have a delta V which is negative, such as in this case, work is going to be positive, which again makes sense because work was done on the system. So we've added in energy to this particular thing. Um, so that's why there's this negative in this equation to account for the delta V um, change sign in order to get the correct change for our work. Okay, so let's see how we're doing so far with kind of thinking about signs um, for work and heat. Excuse me. So let's say we have a reaction. We have A plus B, they're both gases, and they combine to produce C, which is a solid. Okay. And this reaction is in a piston like we see up here. Okay. So we're going to have something that's going to start out with a fairly large amount of volume. And then as we lose the gas, it's going to compress down. So work will be done on the system. Okay? So here we have this reaction, and it loses a total of sorry, loses a total of 1150 joules of energy in the form of heat. And because it loses it, it's going to be a negative value. And then because we're pushing down, work is being done on the system. And in this, our work is a positive 480 joules done on the system. So if we want to figure out, what our delta E is in this case, we take our heat plus our work, add them together, giving us negative 670 joules of energy. And because this is a negative value. This would be exergonic. And because this is negative, it would also be exothermic. Okay, that's it for this particular lecture video. I will see you guys in the next one. Bye.